Our today's topic is eigenvalue, eigenfunction, and eigenvalue equation. Here we explain eigenvalue, eigenfunction. These are included in a eigenvalue equation. Eigen is a German term, German word, and its exact meaning is proper or characteristic, proper or characteristic value or function. Now, how we get the proper value or proper function in eigenvalue equation? Once we explain eigenvalue equation, we use dynamical operators in the quantum mechanics and the well-behaved function psi. Why it is a well-behaved function? Since it satisfies all the conditions. That condition we discussed earlier means function must be continuous, single valued, and finite. Such a function we use here. Firstly, we write the eigenvalue equation. The equation is operator A psi of x is equal to lambda psi of x. Now what each and every term represent in that equation? A is an operator. Operator means it is a mathematical rule. That here this rule we apply for a given function psi of x. Psi of x is a well-behaved function. Then if the operator which operate on a function psi of x, then we get similar function. Means function remains as it is, it doesn't change. And it multiplied by a constant term. That constant term lambda is an eigenvalue of a given operator A. And what is psi of x? Psi of x is an operand and it gives the eigenfunction of a given operator and eigenvalue lambda. Now, how we satisfy this equation? With the help of some general examples. That examples we writing here. First example, if psi of x is equal to exponential 2x and it is operated by an operator d square by dx square, then how that function satisfy the eigenvalue equation using the operator d square by dx square. Hence d square by dx square is a operator. That operator operate on a function psi of x. Then we find its result. D square by dx square exponential 2x equal to d by dx of differentiation of exponential 2x is 2 into exponential 2x. We again differentiate the same term. We get 4 exponential 2x. Then it shows here the operator d square by dx square when operate on the exponential term, exponential 2x is a function, then the function remains as it doesn't change. That function is an eigenfunction of a given operator and eigenvalue 4. Hence operator is d square by dx square. Exponential 2x is an eigen function of the operator and eigenvalue. Eigenvalue is 4 and it satisfies the same equation. Therefore, given function when operate on d square by dx square, it satisfies eigenvalue equation. Second example. Before second example, we explain the same term here. 4 is an eigenvalue of the operator d square by dx square, and the operand exponential 2x is an eigen function of the operator d square by dx square, and therefore this equation satisfies eigenvalue equation. Second example, if psi of x is equal to psi of x is equal to sin x, and operator we choose here is d square by dx square, then what is the result? D square by dx square sin of x. Now what is the derivative of sin x? D by dx of sin x, cos x, and the cos x term is again differentiate d by dx, then you will get minus sin x. Here sin x is a function. That function remains as it is, and it multiplied by scalar term or constant term. That constant term is minus 1. Minus 1 is an eigen value of a given operator, and sin of x is an eigen function of the operator and eigen value, and therefore it again satisfies eigenvalue equation. Now we find in quantum mechanics the dynamical operator also satisfies the eigenvalue equation. Now here are some dynamical operators. Which dynamical operator? Linear momentum operator. We write Hamiltonian operator, energy operator, position operator, potential energy operator, and so on. We see only some examples here in the quantum mechanics. First operator we choose Hamiltonian operator. That operator denoted by H cap. Hamiltonian operator is a total energy operator, sum of kinetic energy plus potential energy. If such a operator operate on a well-behaved function, psi of r is a three-dimensional term equal to E psi of r. E is the energy psi of r. It satisfies eigenvalue equation. It means Hamiltonian operator operate on a well-behaved function. Then we get the similar function multiplied by constant term. That constant term is an eigenvalue of a given operator, and psi of r is an eigen function of the operator, Hamiltonian operator, and eigenvalue. Second example, linear momentum operator. We write x component, y component, and z component operators, momentum operator. That operator is px, x component. Its value you know, minus ih cross dab of dab x. That is, this is the x component linear momentum operator. Similarly, what is another component? Py. Its value is minus ih cross dab of dab y. Pz component operate. It is also z component linear momentum operator. Its value is minus IH cross dabba of dabba Z. Now here we write firstly the eigenvalue equation. Put the value of the operator Px minus IH cross dabba of dabba x. This is an x component linear momentum operator, differential operator, which operate on a function psi. Then function remains as it is, multiplied by constant term. That constant term is known as eigenvalue of a differential operator, and therefore Px is an operator. Similarly, Py and what is Pz? Py in the similar manner, minus IH cross dabba of dabba y is y component differential operator, operate on the psi. We get constant value Py. Hence, what is the value of eigenvalue of that operator? Minus IH cross dabba of dabba y. Psi is operating on the both sides, that is constant. Similarly, z component minus IH cross dabba of dabba z, which operate on the psi, we get Pz psi. Hence, Pz is an eigenvalue of the differential operator minus IH cross dabba of dabba z. Instead of minus IH cross, we also use h cross by I. Since if we multiply numerator and denominator, I. Therefore, numerator term becomes I square. I square is minus 1 minus minus plus h cross by I. Hence, instead of minus IH cross, we also use here h minus IH cross replaced by h cross by I. That is also correct. Next one. In the 3 dimension, what is linear momentum operator? P operator 3 dimension minus IH cross del operator. That del is value is I dabba of dabba x plus j dabba of dabba y plus k dabba of dabba z. Therefore, in the 3 dimension, the linear momentum operator is minus IH cross del, which operate on the psi. Function remains as it is, only multiplied by constant term. That constant is the momentum operator. Hence, this is a 3-dimensional momentum operator. Now we use another operator, energy operator. It also satisfies eigenvalue equation. What is that energy operator? We also find earlier. IH cross dabba of dabba t is an differential operator with respect to time t, which operate on the psi. IH cross dabba of dabba t of psi is equal to E psi. Function is same, multiplied by constant value. That constant value is nothing but eigenvalue of a operator minus I plus IH cross dabba of dabba t, and psi is the eigen function of the operator and eigenvalue. Here these are the examples we use in the quantum mechanics, and they satisfy eigenvalue equations. Thank you.